So let's wait a minute until all the people, well, or I hope some people will join us. One more. I think we can start now. So yesterday we were starting this part, which is how to use convolution in order to, well, to prove some nice properties about well, density of regular functions and well, also some compactness estimates. Okay, so the fundamental tool was the following theorem. Wait a minute. Which was that if we define evaluated in x, so this new function is the integral and we assume that f is in L1 and g is in P, then okay, f convoluted g is in LP. Actually the norm okay, so it exists, is defined almost everywhere, and you have this estimate. So this was the tool. Okay, so I don't think this corollary is interesting. So now we need an additional technical part because so the idea, let me say the idea here use the compactness in, okay, for example, C compact of some compact subset of Rn. Okay? So here we live not in a general measure space, but here we live in R capital N. And the idea is that, well, we need to exploit this compactness, which is the Ascoriazera Theorem, in order to gain results over the LP spaces. So if you look at this function, well, in some sense it's easy to see, we will prove it, that if f is, for example, regular, well, then the function, the convoluted function is regular, because the derivative, when you take the derivative, okay, here you have to use, for example, the back-bounded integral, bounded convergence, the back-bounded convergence, dominated convergence, and then you pass the derivative over here. So the derivative of the function is the function convoluted with the derivative. But there is still one part, which is the compactness. So we need to exploit the compactness. And from this formula, so the part of regularity, one can in some sense, imaging, but how about the compactness? Okay, so this is the part. So we need to speak about the support of a function, but a function which is an equivalent class, so it's not a real function, no? So, well, now it is natural. If I write the definition, you see that it's natural. So the definition, the support of f is the smallest closed set such that as an equivalent class, f the complement in the complement. And so the fact that this definition is well posed is not as trivial as the definition of support for general topological space. Because in that case, it's just that intersection of closed sets, no matter how many it is closed, by definition of topology. So here we have to prove, or the remark, we have to prove that, okay, if as an open set is the union of some uncountably many open sets, such that f restricted on the open set of alpha is equal to 0 almost everywhere. And okay, the measure is Lebesgue here, no? If I don't write anything, I will not write anything. We are living in Rn, and the natural measure will be Lebesgue. Then f is equal to 0 on O almost everywhere. Okay? This is general false, but in Rn it is true. Because, just observe, that in Rn, any open set is a countable union of balls. So countable. And then, okay, and then f on each ball, so because it's 0 on, well, in the union of, so it's 0 by definition in each of the ball, which are the complement of the support, so is equal to 0. So in some sense, well, if I choose the right sets, I'm fine because I need just countably many. Okay? So this is the definition we will use. There is no much difference. Just you have to think that is not f is equal to 0 is the equivalent class in some sense. Okay, so now our aim is to deduce some compact support from the support of these two functions. So I state this as a proposition. Support is contained closed. Okay, if one of the two is non-compact, I cannot state that the sum is compact. So I need to take the closure. So why is that so? Okay, let's see the idea. The idea is that I need to have that X, so this is a sketch of the proof. So this object here should not be 0. Okay, So I define, for example, that I choose the two functions such that they are 0 outside. So outside the support. They are in equivalent class, and the integral does not change. So it should be f. So I'm studying something which is even larger than the support. Because I define f and g to be 0 outside, and well, I'm saying, suppose that that guy is not equal to 0. Okay, let's look back. So from here, it means that, well, fx minus y, okay, cannot be 0 always, no? Okay, so in my definition, it means that x minus y then belongs to the support of f. Because I choose the representative that is 0 outside the support. Well, the same thing, then gy cannot be 0. Or at least the same y. So it means that y belongs to the support of g. If I add the two facts, then x belongs to the support of f plus y, so belongs to the support of f plus the support of g. So with this particular choice, if the integral is non-zero, for sure x belongs to the this set, the sum of the two supports. So there is a one, let's say, y here and one z here, and they is equal to x. Otherwise, it is 0. And then this is done because now I just proved that the support of f, not as a function, not as an equivalent class, but as a function, is contained in these two sets. Okay? So the support being closed, I need to take the closure. That's it. Okay, so now we start with the regularity estimates. And annotation here is that, well, when I say L1, let's say LP lock of Rn, it means that, okay, all the functions, let's say all the function G measurable such that G restricted to any compact sets belongs to LP, okay, of the compact set for all, well, no, for all bounded sets actually. But I take just compact is okay. Okay. So let's start with the first regularity here. Now let's F is C compact of Rn and G. Okay. Now if F is C compact, you see that what I need in this theorem is just that, well, for any x, y should be in a compact set, because it is the translation of the compact set by x. So what I need just in the estimate, in order to give to have the well, to have that convolution theorem, is that G is in LP lock of Rn. So let me put a remark here, so that is defined. What is the idea behind that is lock? Then is continuous. proof. I think that this is these are just the major theory proof theorems, no? Because well, x maps to the integral of f of x minus y dy.
Moreover, if convolution G is uniformly continuous, I think it's
uniformly continuous because this is uniformly continuous. Yes.
Compact. Yes, compactly supported function. So it's convolution.
But wait a minute. There is to be careful here. Is because you are not adding information because when I estimate the limit, I need to know this object here, no?
Yes, yes.
And then it's only locally.
But we can suppose G just LP function because F is compactly supported, so without loss of generality, we can suppose G
Infinity plus infinity, then you don't say anything. But otherwise, you cannot know because the GY, its norm, can grow when you go to plus infinity, and then, okay. Here, if you want to estimate, well, the limit is the Lebesgue-dominated theorem. In order to prove the continuity. Okay? I don't say anything, it's just that this is bounded, and it converges pointwise, and this one is bounded uniformly. So you just pass to the limit by the dominated theorem. So you ask about the continuity. However, if you want to say how to estimate f of x minus y, x prime minus y, gy dy, well, and then you say, okay, this is less or equal than what? The modulus of continuity of f, and then you get the integral of gy dy. Okay, and then you can say in some compact subpair, which is the support. So it is x, so the two integral is x plus the support of f, union, let's say, x prime plus the support of x prime, of f. Okay, the two sets where it is not 0. But the problem, you see, that in the moment that x and x prime, they remain close, but they go to plus infinity, the object over here, you don't have any bound. So it's not, you don't gain anything here. It's just continuous. Continuous functions are locally uniformly continuous. So this is just the answer to the question. So corollary of all these things. F belongs to CK of Rn, G belongs to LP lock. Then, well, what you expect to be. So F convoluted to G belongs to CK of Rn. And, okay. So the thing is just, is always this passage to the limit, no? So the pass, when I pass to the limit, let's do the proof, and it's just one line. So I need to compute the limit of f convoluted g, x plus h, x, h, and this is the limit by definition. So if I go inside the thing, is f x plus h minus y minus f x minus y over h dy, g dy. And now, since I assume that this is in CK, they converge pointwise or uniformly, doesn't matter, but this guy is your bound as before, And so the limit exists by dominating convergence. And so now, if the limit exists, it's converged to the derivative, and in general, the multi-index alpha derivative is d alpha convoluted with G. Okay, I don't know if you know the notation with multi-index or not.
No, Professor.
You don't know, so the notation. Sorry, you know or you don't know? I didn't hear very well.
No.
No. Okay, notation. So alpha wants to express alpha is a multi-index, so alpha is alpha 1, let's say alpha 2, alpha n. And what does it mean that this notation, the alpha f, is d over x1 taken alpha 1 times, d over x2 taken alpha 2 times, d over xn taken alpha n times of f. So is the multi-index notation in order not to write every time this, let's say, this vector in n to the power, in the natural number to the power n. Just say alpha is a vector in n to the n. And then this is the observation. So this is the short notation. Okay, so far so good. Now let's go back and we now take a very important tool. So we consider a very important tool here, which is the convolution kernels. What the book says, modifiers. But actually, in other places, they're called convolution kernels. So, definition. So, is a family of functions. So, rho n is natural, is a family of functions contained, let's say, in C infinity compact of the unit ball. So C infinity of the unit ball closed. So let's say norm of x less or equal than 1 with values in R.
Are these also called approximations of identity?
Yes, these are approximations of identities because well, we will see that the convolution, it converges to the identity operator on LP. Yeah. Well, I should say that approximation of identity never enter into my language, but usually what I say is convolution kernel, because I use it as a convolution, and the kernel means that when you go to 0, you get the identity. Okay, so such that, so 0, so they are larger than 0. Let me see, and the support of rho n is in the ball. Well, now you can choose whichever factor you want to put here. So the book chooses 1 over n, and the integral of rho n equal to 1. Okay, I'm not going to say that such a function exists, because the easiest way to build is that take a function rho 0 in C infinity with the properties that you need. Greater or equal than 0, and the support of rho 0 is in the unit ball. Okay? Then you scale the function in order to concentrate it, no? So let's say rho nx times n to the capital N is your rho n of x. So what I'm doing, you just concentrate or rescale x in order to make the support the ball over 1 over n, but in order to have the integral 1, you have to put a factor in front, which is just the change of variables. Okay, so let's start we want to see now what happened when instead of f here, I put one of these convolution kernels. So if f is continuous in Rn, then rho n, okay, let me write it here. Solution f converge to f uniformly in compact sets. Okay, everything comes down again to the formula. There is no much than this. No much more than this in many computations we do. Well, of course, because this is the formula. But what I say is that at the end is always an estimate on, or a formula like this one. So the difference of two the function evaluating 2 points while you download the difference into one of the function, then you keep the integral. So the formula is already here, where now G will be rho n and this will be f. Okay, so let's do the proof. So if you fix any compact set, for example, so fix the ball of radius r closed, so that, let's compute the convolution rho n convoluted f in x is the integral rho n, and okay, here I prefer to change variable. It is clear that if I define this guy to be y, then this becomes x minus y. Okay, so it's equal also to the integral f of y g x minus y. So in some sense, I can choose on which part of the function, which function to charge with the variable x. Okay, and here I prefer the other one. So because this guy here, clearly, if you see by the example, but of course this is true in general, because the integral is 1, this cannot be a uniformly continuous family. So if I want to use it as in order to estimate the different x minus x prime, or in this case the difference of the two integrals, I get something which is not particularly nice. So now this is wait a minute, because maybe I'm saying something. Oh, no, okay, sorry. Here you don't need that. I'm sorry. Here you don't need it. It's in a later one. So let's use the standard one. X minus y, and then this is f of y, dy. On the other hand, f in x is the integral rho n x minus y f of x dy, simply because this is constant and the integral is 1. So I get rho n f in x minus fx is equal to the integral x minus y, and now the difference. So it is fy minus fx dy. Okay, yes, I don't know. In my notes, I put this guy, but I think it would have been better to just... so now, I change variable, sorry, it's easy. Rho n y f x minus y minus fx dy. Okay, and now you see. So, this was this observation here. So now, for any x, the y that I consider, they belong to the neighborhood of radius 1 over n of x. Because otherwise, well, this guy is 0. Okay? So this is estimated in a neighborhood of x of radius 1 over n. So if I live in this compact set here, then x minus y belongs to the unit ball of radius, okay, r plus 1 over n. So it's a family of shrinking closed sets. At the end I get, okay, in particular, if omega is the modulus of continuities of f in that compact sets. Okay, they put plus 1, so I don't have to care anything. So what I get now from this formula, the modulus of, let's say, f rho and convoluted f, okay, I can take really the norm, minus f, is less or equal than, okay, is the modulus of continuity, which is omega of, at most, y as radius 1 over n, so omega 1 over n, and then I get the integral of rho n here, which is 1. Okay, so essentially, this is important. It's a remark. It's not in the book, but in general, and one of the problems one have to be careful is that convolution is you always enlarge a little bit the set under consideration, no? So the set of values used by, let's say, it is convolution kernels is actually a little bit larger than the set under consideration. And now the thing is that, so it is slightly larger, and indeed there are, here we are in a nice setting that you can enlarge it and still you have the property you're looking for, or vice versa, you need to shrink a little bit the set that you consider in order to be sure that the values are inside your original sets. So this is a by-side remark, but it happens a lot. Now we define why it's called approximation to identity or convolution kernels. Okay, but since you have done measure theory, you know that what happened is that rho n as a measure, so Ln, converges weakly in the sense of measure to the Dirac delta in x equal to 0, no? This you know. Is level 0. So now you see that this convergence, well, uniformly, but the convergence is just, if I don't say uniformly, is just because of the weak convergence of this to the measure, to the Dirac delta. Because if I convolute it with the Dirac delta, by definition, so is the value of the function where x is equal to y, or y is equal to 0 in the second form. So, theorem. Okay. If f is in Lp of Rn, and now I need to remove infinity because the infinity norm is too strong. It never works. Never works. Then f convoluted, sorry, rho n f converges to f.
Almost everywhere, not everywhere.
Pardon?
Almost every point, not every point. In the points of Lebesgue points of the...
Yes, but this is in Lp. I forgot.
Yes.
It's in Lp.
But point-wise convergence we also have.
We have also convergence for Lebesgue points, you have pointwise convergence because, well, you can see as a consequence of, well, if you estimate the integral is minus this guy minus this guy is exactly by definition of the Lebesgue point. Not okay. So we use the density of, okay, here what I say, Cc over n into Lp. Okay, and this was one of the results we had, I think, yesterday, or it is a result in general measure theory. Think the way that you prefer. Okay. So now what is the trick? So I need an estimate on okay, I know, I think, I don't know, it's, okay, let me do it. So let's write. Rho n convoluted f minus f in Lp, we write into 3 pieces. So it's rho n convoluted some f tilde, and f tilde is in C compact. f minus rho n convoluted f tilde plus, and now I have the translation, I pass to f tilde to f, and then I have what is the remaining, which is f minus f tilde minus f. Okay, just add and subtract the same terms. Now, this guy is, the convolution is a linear operator, so it is so rho n convoluted f minus f tilde plus, okay, what is left, rho n convoluted f tilde minus f tilde, and, okay, the last term, f tilde minus f. And now the passage is that, remember my estimate, that is the Young there, so the LP norm here is bounded by the LP norm of this guy. And indeed this is the nice property, so the convolution is one Lipschitz, a linear operator, and also one Lipschitz, very well. So it is less or equal 2 times this guy and this guy. So this guy is controlled by this guy, so it's 2 times this guy. Plus, and now I have this thing. Very well. Well, now by the density, I can make this as small as I want. So this is very small by density. I can choose an f tilde such that this guy is very small. And this is very as small as I want by the proposition. So I can choose an n such that this guy is as small as I want. Okay? The corollary of this, so now we see why it is so nice. The corollary C infinity compact over n is dense in LP. And, well, the difference between this result and the result that I'm using here is that this holds for, even topological space where the sigma, well, you have some, so for example, metric spaces, they work. But in metric space, you cannot take derivative in R, and the structure allows you to prove this result clearly with the right measure, because otherwise you cannot do that. Okay, and okay, why is that so? Because well, we know that if you the convolution of a function is as regular as this guy, and this guy is in C infinity compact, so it's a C. So essentially, the approximation that I'm building here actually is C infinity compact. And so the other result, another thing that is trivial in some sense. F is in L1 lock over n, and the integral of fu is equal to 0 for all u, which is in C infinity compact over n, then f is equal to 0. Well, it's almost an exercise, because we have the density, and it means that this is 0 for also any function, or you can make an approximation, then choose So there are a lot of proof. I'm not going to say anything. Okay, and now we are ready to do the important theorem, which is the compactness of LP spaces. I think today maybe we're going to finish a little bit earlier. So there is a nice criterion which allows you to determine if a set is compact or not. And the basic tools is the Ascoriazera Theorem, which I hope you know. So this regards the compactness in CK, where K is a compact set, no? So, bounded and
Uniformly continuous.
Pardon? Very difficult to interact in this way.
Uniformly continuous, then it is relatively compact set. H is relatively compact.
Yes, well, okay. Yes, if I say it is closed, it's uniformly continuous. Then, okay, the H is relatively compact or equivalent is pre-compact. I think it's called is pre-compact. So the closure of H is compact. You know this statement?
Yes, yes, we know.
So have you done in a previous course?
No, we studied in undergraduate.
So I don't understand. Does anybody know the statement or?
I don't.
Not all of us
don't.
do.
Okay, so I will sketch the proof. And okay, and let me say that here K should be metric. Okay, let's do the proof. The proof is more important than the compact statement on LP. Because let me make it, okay, let's do this. Let's do first the sketch of the compactness in LP. And then we will address the theorem. So let me go to the statement. Theorem. So now we want to have the other theorem. Let me grab it. I don't want to say in the wrong way. So it's F LP of Rn is bounded. And okay, P is 1 and infinity, such that so the translation is uniformly continuous. So in LP, so let's say the limit for H that goes to 0 well, that tends to 0, doesn't matter in which sense, the translation. So it's f x plus tau minus f x. So this should be the integral norm p in dx. This goes to 0 uniformly. So there exists, so what does it mean uniformly in f? So if tau is sufficient for having epsilon, you can choose h, so this is h. You choose the modulus of h sufficiently small, and then the LP norm of the translation minus the original function is less than epsilon, no matter which is f. So maybe I write it. Oh, okay, that's the conclusion. The conclusion is that then f is pre-compact, which is, it means that the closure of f is compact. Okay, in each set of finite measures. So let's do the following. So this is not the nice way to write it. F in F, let's see, sorry. These chocks are very bad. F restricted to omega, well, F is in F, closed. So these are the restriction of the function to omega, and omega as finite measure is compact. Okay, so this is the statement. It's a little bit strange, but I need in any case I work in Rn, I need in any case some compactness, because otherwise if I repeat this guy where instead of k I have Rn, it's false. So the compactness is set as the omega who has a finite measure. Okay, let's do the proof of this thing. So what is the idea, in your opinion? Well, it's written here, more or less, what we are going to do. So we have two facts.
Density of infinitely differentiable functions compactly supported.
Yes, so the idea is that if we take convolution with a fixed n, then by this theorem we get a set which is as close as we want to our original set. Okay? Vice versa, so if we go to the explicit estimate, which is written basically here, I discover that if I go to something which is probably been cancelled and is, was the previous, I discovered that for any fixed n, these convolutions are uniformly Lipschitz. Okay. And then to have the compactness, well, I need to use that the set omega with whose measure is bounded is almost a compact set. I can remove in a small set, and then I'm fine, uniformly. And finally, with these two things, essentially, I'm saying that your set can be approximated in norm by compact sets, because of the compactness of this guy is deduced by Ascoriazera, and the C infinity norm, the C norm, sorry, the C0 norm is stronger than the LP norm. So, so the conclusion now is that I need to use another tool. I'm sorry. If you have these approximation properties, the your final set is well, there is a notion I have to introduce, totally bounded and it is compact. So let's do the proof, sorry. Okay, here what I do is, I think I'm not the best here in this proof because I get a little bit confused. Okay, the first thing is the following. So, step 1, estimate rho n f minus f in LP. Okay, this is what it's, let's go. I have some formula somewhere, or maybe I already erased it. So this is equal. Okay, the two things is equal to the normal P of the integral rho n y f dot minus y minus f dot dy LP. You remember, I can write this one because the integral is 1. And now I know that this guy is continuous. So for each y, the LP norm of this is bounded by, okay, let's say this modulus of continuity, omega of y in LP. So I have that the norm of f, the translation minus f LP is bounded by this guy. Okay? So when I take the LP norm of the convolution, this is just, I can apply Fubini or can use whatever, I get that this is less or equal than omega, sorry. So this is omega of the maximal radius, which is 1 over n. And so I deduce that the convergence is uniform. So this is the first step. So the difference between the convolution and f is uniform no matter which is f. So the second, so now I need to make use of that rho n. So it's the derivative, let's say, the gradient of this one is the gradient of rho n convoluted with f, and this guy clearly is, so all these sets are uniformly Lipschitz because it's bounded by some constant Cn, and then, okay, well, there is still one piece because, well, if the omega is bounded, be the some constant, and then, okay, is the integral of f over omega. And here I have still to be careful. I'm a little cheating here because there is what I said before, there exists the fact that you take points slightly outside omega. So I want now, but let's see. I want to make use of this fact, and then these functions are okay, satisfies Ascoriazera. By Ascoriazera. Okay. So the second step is this one, and then I need to make use of this thing over here. because I'm taking the proof in a strange way now, and okay. So 2.1 as an additional point, 2.1. So the measure of omega is omega, or there exists a
Compact sets inside.
yes, there exists a compact set, I'm sorry. So let's say Lebesgue is inner regular, which means that the measure of omega is the supremum over compact sets containing omega of the measure of K. Okay? So there exists a compact set such that, let's say, omega minus K is less than epsilon. Let's use, then epsilon will be fixed later. So now I want to say that since I live in so I want to remove the set which is out outside K. I'm sorry, I'll take in the proof in a strange way, and now I forgot. There are two facts, so I want to say that the measure, let me see 1 second. 1 minus K, because I need to use IC in LP, let me see just 1 second. Okay, I just forget. Yes, because I changed the line of the proof, and then I'm confused because at least I have to do a little bit later. Sorry, let me restart. I need to do something earlier, and then oh no, okay, it was okay. Okay, so this epsilon is connected to the previous epsilon. So the fact that this is less than epsilon. Okay, how to prove that? So now I want to prove that f p integrated in omega minus my set k is less than okay, let's estimate. This is equal to the integral f minus my convolution to the p, so to the 1 over p, let's say. So the norm, and this is omega minus k plus what is left, which is the integral f rho n f to the p, 1 over p in omega minus k. This guy is less or equal than epsilon because it's less or equal than the integral of the whole space. And then plus, so this guy, rho n, is uniformly bounded, so I can take epsilon if, so less or equal than the norm, let's say of this guy infinity, which is essentially is 1 over n of the order of 1 over n, the norm of f, Lp. Well, there should be some factor here, let's say. So let's see, to be correct, you can compute it, let's say it's the norm of rho n convoluted f infinity, the measure of omega minus k. So I get with all of that less than 2 epsilon. Because I just choose with this property, this guy is less than epsilon over the norm of rho n f infinity. Okay, so now what I have okay, so now let's go here. So I have that in this, let's say, compact set K, I have a family of functions which are, satisfy Ascoriazera Theorem. Okay? So in particular, I deduce that convoluted f with f in my family, and this is restricted to my k, is compact. So this is the third step. It's compact in C0 of k. So in particular, what I have is that so the C0 norm is clearly stronger than the LP norm. So it implies that it is also compact. Is also compact in LP of k. And then, well, I can extend them to 0 outside, so it is omega extending to 0 outside. So what I have now, I have proved that you have a family of compact sets. So we have, okay, family of compact sets Kn, 1, such that the distance for any f, the distance of f to Kn is less than, okay, and then I can choose n and the epsilon, so let's say it is 2 to the minus n, doesn't matter, it's just a choice. Before I choose epsilon to be 1/3 to the minus n, and then I choose n accordingly. Okay? So now I'm saying that this implies, I do like this, and this is, so this implies f is totally bounded. And it means the following, that for all r, okay, there exist, for all r, there exist finitely many balls B centered in some, okay, Fi of radius r, such that F is contained in the union of these finitely many balls. These are balls in LP. And what we are going to see, I think, well, let me see if to do it Friday, or we can see later, is that this implies metric space, this is equivalent to precompactness. Okay, so now we are going to prove that this property you have that F is totally bounded. I think this is a one-line proof, if I'm not mistaken. Okay, so so consider a covering. So fixed. So here the radius R, and cover take Kn such that this distance is less than R third for all F is less than R over 3. So now cover Kn with balls of radius R over 3. You have finitely many of them because it's compact. Now, by definition, if you increase the radius by 3 times, okay, let's say that this balls Bi, so let's say Bi of some point Fi radius R over 3. And now the balls B Fi of radius R cover F. Because if you have this distance, so there exists an F whose, so here you have a point whose distance is at least 3 over R over 3, is less than R over 3. And now you have a ball which contains that point. So if you enlarge the ball 3 times, it contains certainly F. Okay, so let me collect all the stuff. So the proof works because you have this uniform estimate. So you know that the distance, so there are some ingredients. Some are quite trivial, and is the fact that the regularized set construct a compact subset of F. Well, we know from the theorem that this compact subset will converge to F because point-wise this guy converges. But the advantage here is that the first estimate gives you an uniformly convergence, and is very close to Ascoriazera in some sense. And then when you have these 2 things, the remaining part is to prove that the property of finite covering with balls is equivalent to precompactness. And in metric spaces, well, this is done by, for example, they are proved by sequences. I'm not going to do that. I discuss first Ascoriazera. Then maybe we will do the last part. So with this in hand, now we want to discuss Ascoriazera.
I think second side of this theorem also works. Namely, this one is criterion for
you mean by inverse, inverting the theorem?
Yes, namely some subset will be compact set if and only if.
Well, you have to specify this guy.
If and only if it's Arcellascoli for Arcellascoli. No, for no LP.
No, Ascoriazera, yes. If it is a compact, then it is uniformly continuous.
Yes.
Yeah. And this guy is almost the same, but you have to replace this condition with something. So how to define that? This goes into not the statement, it goes into the hypothesis. And then you have to say what is it. Okay, so let's do this compactness in CK. So the assumption is that the assumption there exists omega, which is the modulus of continuity, for which, let's say, for all u of x plus h minus u of x, omega of h. Okay, and well, sorry, I'm already working in Rn, otherwise should be different, no? So if I work in a metric space, it should be that u of y, u of x, omega, that the distance x, y. Now K is compact, metric. In particular, it is separable. So we have this dense sequence, no? Well, it's because you take the ball of radius r, or 2 to the minus n, and then you take finitely many points. So the collection of all these points, which are the center of these balls which cover K, is clearly countable, and by definition, it is dense. Okay, now what we do?
Why u will be, v is Lipschitz function? You satisfy the Lipschitz condition. Why it's satisfied? Why?
Well,
is it satisfied? Lipschitz condition.
Here?
Yes.
No, omega is a function.
Omega, it's different.
The modulus of continuity can be square root or even worse, just something that goes to 0. No? So now okay, I will do something later. I take that this is closed. So I take a sequence here, and I want to prove that it has a convergent subsequence, which is the same as saying that the closure is compact. Let un belonging to H, and what I do take subsequence, say un I, such that uni of xi converge to some value, which we call, let's say, it's a function of a value, which I don't yet know it is a function, well, but it is a value. I define this value with this notation. Now I can repeat for all xi, because then I take subsequence of u and I converging on x2. So at the end, with a diagonal process, so I obtain there exists a sequence which, I define again un, let's say um, or u tilde n, so it is a subsequence. Converging for all xi. So at least I have defined this limit function on uxi. So let's say um converges to uxi for all xi. Now the problem is to prove that this function has a continuous extension, and it is the limit. So let's see the uniform continuity. By uniform continuity, I get that umxi minus umxj is less or equal than omega, the distance xi xj, because it holds for all functions. So pass to the limit. Get that uxi minus uxj omega xi xj. So what I deduce that if xi converges to some x in k, then from this relation uxi converges to something, some number, which I call u of x. So in particular, u can be extended uniquely on k. There is a unique extension if I know that it is continuous on a dense set. Well, this is the trivial thing. If I know it is a continuous on a dense set, that there exists a unique continuous extension. So finally, how to prove that you have the strong convergence? So finally, let's go here, and this is the last. If you want to try, you can also repeat this idea here, no? So finding some balls which contain all the functions. I think this is more straightforward. I don't know. So finally, u m of x minus u of x. And now this guy, it's I cannot use the result here because x is not one of the sequence, no? But however, is less or equal than the distance xi x minus um xi plus umxi minus umx plus, uxi minus ux. And so here is the continuity, omega xxi. This guy is the limit. So this is epsilon for m sufficiently large. And this guy is again omega. Okay, and so this estimate, it means that if I take, I choose a point such that this distance is less than epsilon, then I choose m sufficiently large, I get at the end that this is less than 3 epsilon. So it is uniform. Okay, I think there is no time to discuss because how to remove, how to invert this theorem. Okay, it's easy instead to see that the converse is true because it's an exercise to prove the following. And the thing is already here. If let's say un converges to u and u are continuous, then un is uniformly, so the sequence continuous, which is in some sense the inverse. Actually, this is the inverse of the theorem, and the estimate is exactly this inequality here. No? Well, because now I'm not using, so I'm estimate here I want to estimate this guy. And I'm using this guy. And the rest is small because it converges. So I know this fact. What I don't know is this estimate. Okay, I think we can stop here because the other part is important, even if it maybe is elementary. And so just one question: have you seen tightness of well, functions or measures? The concept of tightness.
Tightness, what?
Tightness, yes.
Don't think we have seen. I have never seen it.
You know?
No.
We don't know, I think.
No, okay. This is another important thing, so it's better to see next time because it's... so have you seen Vitaly Theorem, which is an extension of Lebesgue?
Vitaly covering lemma.
No, the the Convergence Theorem.
No.
No, okay. So I think because the concept of tightness is the one that enters into inverting this assumption here. So, okay. So I can say that the idea of tightness is that if you think as this function as measures, so the measures can disappear in two ways, essentially. Well, actually, the mass of the function can disappear in two ways. So the first is that you move the mass to infinity and along the horizontal line, and the other is that you move the mass to infinity along the vertical line. Then it becomes a singular measure, and as a function, you don't see anything. So the tightness is exactly saying that your mass stays bounded. So you cannot lose mass with these two procedures. And it is an extension of the Lebesgue-dominated convergence theorem, because the Lebesgue-dominated convergence theorem, the tightness is for free because of the uniform bound with an L1 function. So let me stop here, but okay, it's perfect. So next time we will analyze this concept and we will invert the theorem. So are there questions? Not. So, okay, I already say that if you need anything, you just can contact me, and then we will try to the situation. So about the course, so I think we are really in time to do the whole thing, and then the last days we will do some exercise, example of written examination samples.
Thank you, Professor.
Welcome.
Thank you.
I know it's very hard for you, and I'm sorry.